Welcome to this math reading group on category theory. Um, so don't worry if you haven't managed to get through the papers or any reading for today. I somewhat expected that, so I'll be a bit pedagogical today. Well, I guess as pedagogical as I am usually. So um, yeah, so roughly what we'll be talking about today is the applications of category theory for machine learning, but I'll need to get through a bit of background, but I'll only go through like the minimum necessary that I thought was needed for today. But like I felt like especially with category theory, I needed to motivate why you would want to learn it or use it. And so because famously category is so abstract that it has no application. It's like useless. But it's not entirely true. And so I could ask you, okay, why, if someone asks you or me, why do you need category theory or why do you think category theory is useful? Well, I could say, and I guess because most of you, most people here are like computer science people, programmers, and so on. I could ask you, well, why do you need type systems? Why do you need functions? Why do you need compilers and so on? And when I say type systems, I mean stuff like you would find in like the Haskell type system, which has like algebraic data types, polymorphic types, or like generics basically, type classes and so on. So like any kind of type abstraction that a language has. And probably your answer would be, well, I don't strictly need it, right? I could just like write my entire all my programs by hand in assembly, but that would take a lot of effort, a lot of time, and really does not give me the right level of abstraction to be thinking about what I want to think, which is, well, I want to optimize neural networks and perform gradient descent with computing the gradient automatically and so on. So you have different levels of abstraction that you're trying to deal with. And so the answer here that you don't need abstraction, but it's very useful. It makes your programming easier, it makes verifying that your programs are correct easier, and so on. And category theory is really all about abstraction and this sort of stuff. So most of the applications of category theory, you could say it's about syntax. It's like describing the abstract syntactical properties of whatever problem you're studying and like finding the simplest framework that works. And it's mostly useful if, let's say, you're trying to build a compiler. Let's say you want to build a library that does neural networks, that does backprop, that like does optimization. That's a very complex system. You have a lot of components that you'd like, hopefully, to be able to have like compose or like you'd like it to be modular or composable um, easily, and that you could have a nice fancy compiler that takes your neural network specification and compiles it into an efficient program that does the whole training for you. And that's the sort of what you should expect from category theory, especially in machine learning. It's not about helping you do some calculations. It's about finding or the simplest way to frame a problem and then to design programs to run them. So for today's menu, I wanted to do more than I ended up being able to do, but we'll be talking about like basics of category theory, like as I said, just enough to get the examples going. And then the main example is going to be the second one actually. So like how to model or describe gradient-based learning using category theory. And then I also wanted to cover like automatic differentiation, so backpropagation, but we probably won't have time. But one of the papers I gave for reading was basically an entire paper about using category theory for taking your basic like model, so like the basically the program that describes your inference of your model, and does a transformation to turn that program into a program that computes the derivative or the backprop. And like that, this is essentially what's like backprop compilers try to do. They're trying to take a program that does the forward pass and like transform it to get a program that gives you the backward pass. And this is fairly non-trivial. And so in that paper, the author showed how to do that using category theory in a still abstract and complex way, but like less complicated than other methods. But we probably won't have too much time for that. And then because it's such a meme, I figured it might be amusing, maybe as like a bonus, to explain whatever a monad is a monoid on the category of n factors is, right? So because it's on category theory, we might as well just have a monad tutorial as well. But let's not get ahead. So a category as like the definition as a mathematical object is not something especially complicated. It's like a collection of objects and a collection of arrows. And specifically what means we have like some objects. So this my like C is a bit weird here, but uh, you should think of this as a fancy written C. And I have objects, so A, B, C, and these could be anything I want. Um, Depending on the category, I have different things. And then I'll have arrows connecting my objects, so F, G, and H. And typically, I'll be representing them using diagrams. So for example, the arrow F that goes from A to B is represented as this top here, this top diagram here. And in for my object C to be a category, I need a few operations and axioms to be verified. So for the first one is that for any arrow F, I need to have something that gives me the domain of F, in which case it's going to be A, so like where F leaves from, and then the codomain or the image of F, which is where F arrives. So any arrow has a domain and a codomain, and for any object A, there is a special arrow called the identity arrow that goes from A to A, and we'll see exactly what it does later. And then if I have any two arrows F and G, where F goes from A to B and G goes from B to C, I can compose these two arrows to get G composed with F. It goes from A to C, and this is exactly the same. So taking G composed with F is exactly the same as just going from A to B through F and then to C through G. So it's just I can form these arrows, construct these arrows, and I have just basically two axioms. One which defines what the identity arrow means, and basically identity just does not change anything. So if I had like F composed with the identity on its codomain, that's basically the same as F, and it's basically the same as F composed with the identity on the domain of of F, and essentially. So identity just is like the identity map if you in your space. And then composing arrow has to be associative. So F composed with G composed with H is the same as F composed with G composed with H. And so along as I have all of these things, which is not a lot, it's very simple, I have a category. But it's best at this point to give examples. So the most common or like well-known category is set. So the objects in the category sets is simply sets. So I would have A, B, set of real numbers and so on. So any set belongs in the category of sets. And so the sets are the objects, and then the arrows are just functions between sets. And so they're functions as we know from like a classical math course. So yeah, very basic. And so sets has almost a special place in category theory in the sense that because mathematics is founded on sets, a lot of things in category theory you can translate back into sets. But notice that when I defined categories, I didn't say that the objects and the arrows were sets. So you can have uh, categories where the objects do not form a set. In fact, sets, right, the category cannot form, like the whole collection of sets cannot be a set because you have a paradox there. So you technically have to be a bit careful, but let's not worry about that. Another example of a category is if I take the real numbers with the order relation, so smaller than, and then the objects here are just going to be real numbers, so x with an error, and then an arrow is just going to be given by any relation of the type x smaller or equal than y. And so this might seem like a strange notion of arrow in this case, but you can check that it actually satisfies all the axioms we saw on the previous slide. And like this is the same for any partially ordered set. So any poset set gives you a category automatically. But a more interesting example might be vector spaces. So let's say real vector spaces. So the objects are just real vector space, so R, N, RD, and so on. So any real vector space. And then the arrows are just going to be linear maps between vector spaces. And we have an identity linear map from any vector space to itself, and so on. So it works. And like more generally than vector spaces, any structure sets like groups, topological spaces, differential manifolds. So it's more a lot of like higher level objects in mathematics is defined as sets plus some extra structure. And you can usually define a category of, okay, my objects are my spaces, and then maps are just um, functions that preserve whatever structure I care about in this case. And then a final example that might be more interesting to computer science people is types. So whenever you have a programming language that has types, let's say Haskell because it has a like fairly well developed type system, then you also have a category that describes the types. So in Haskell you have like types like A and B. So like A, so lowercase a is just an object of type A, and uppercase letters A and B are my types, and those are the objects of my category. And then I can have morphism, which is just functions that map from type A to type B. And we'll see examples of, we'll keep this Haskell example for later. So one notion which will be weird to start off, but will be useful later is the idea of opposite category, or also called a dual category, which is basically if I have a category C with okay objects and arrows, I can construct the opposite category, and you can think of it as like the mirror image of C, because I essentially have the same objects, but I'll node them differently. But any arrow gets reversed. So if I have an arrow F from A to B in C, then in the opposite category, I have F star that goes from B star to A star. And why I mentioned this idea of opposite category is that one of the like most useful ideas in category theory is this idea of duality, where any because C is identified like there's a correspondence between C and the opposite category. Anything I define or any theorem I have in C, I have like an equivalent in C up, which I just obtained by flipping the arrows. And so this is useful because usually, um, like when you define one object or one thing in category, you automatically get another thing for free just by flipping the arrows. sometimes you get the same thing, but that's a general property that anything in like the normal world is also has an equivalent in the mirror world, and you can get quite a lot of out of that. And we'll see an example just now. So I mentioned category theory is all about abstraction. So abstraction means going just higher and higher into the tower of madness. And so we had categories, objects, and morphisms. Well, let's now talk about transformation between different categories. So that's called a functor. And so a functor from a category C to a category D is basically two two parts. I need to map objects and I need to map morph arrows. And so we have, if I have the following situation in C, so let's say F that maps from A to B, then my functor is going to map A to F of A, B to F of B, and then F to F of F. And so basically all this situation here gets translated to something on the right. And so this is a functor also called a covariant functor because composition does not get reversed. But you can also talk about contravariant functors where your functor also reverses the arrows. And there's a nice example of that. And the punchline is actually that functors are just mapping morphisms of categories. So you can like imagine a category of categories with some caveats of the actual definition here, and just then functors are just arrows in that bigger category. It's yeah. Let's go through some examples. So the first one might not be meaningful to a lot of people, but let's go with it anyway. So let's say I have a category of discrete dynamical systems where my objects are just sets X and then a map F that goes from X to X. And so I have an example here on the bottom. So X is just the set A, B, and C, and then my map maps A to B, B to C, and C to A. And it's a discrete dynamical system because you could imagine just iterating F over and over again, and that's your dynamical system. And I say I can construct a functor from discrete dynamical systems to directed graphs by taking, so I won't define exactly what a directed graph here is, but um, a directed graph has a set of nodes and a set of edges, and the set of nodes is just x in this case, and the set of edges is the set of pairs x, f of x for all x in x. So those are all my arrows. And in this case, this dynamical system on the right, on the left, sorry, becomes this directed graph on the right. And so this is a functor. I won't prove it, but because it preserves all the properties from discrete dynamic systems and maps them to directed graphs. But note that I can go from left to right, but not necessarily from right to left. So not every directed graph comes from a dynamical system in this way. Another example from linear algebra is basically the idea of dual vector space. So for any vector space, I can like get its dual vector space, which is a bit of the mirror vector space. And this is actually a contravariant functor because it's a functor from the opposite category of vector space to vector space over R. And so if I have a vector space V, my like dual space functor maps it to its dual space, which is simply the set of maps from V to, I guess I should put R here, linear maps from V to R. This is another vector space that has quite a lot in common with the original vector space. And in particular, any linear map, let's say F from V to W, ultimately corresponds to a linear map from W star to V star, defined as, okay, F star applied to G applied to V is simply G of f of V. And so this is like the simplest or most well-known example of contravariant functors. And so the whole punchline that a lot of things in mathematics can be restated in this language, but let's not get too far in there. Another example of a functor that's more familiar is the idea of polymorphic types. So let's say I have a type A, and then I want like the type of arrays or vectors of A or list of A. You can think of list as something that takes a type and gives you a new type. So list of A is a type um, obtained from A. And so list itself is a functor. It takes a type and gives me a new type, and it's in this case in the same category, so we call that a Nando functor. And so list of A, so list is a functor, maybe so like A either some object A or nothing, that's another functor. Okay, um, I'll need to get some more definitions before moving on, but this will be quick. So one nice example of something you can do in category that sort of generalize a whole bunch of things is the idea of products and co-products. And so let's say I have two objects A and B, and then I'm going to say that another object A times B for the product is a product for A and B. If I have some special maps pi of A and pi of B that map from my new object to A and B respectively, and it's going to be a product if for any other object C that has maps like these, then there must be a unique map f from C to A times B such that f of A is simply f composed with pi of A, and same for f of B. And so if you want the like simplest example, let's say A times B for sets would be the Cartesian product. And so let's say I have an object C in here, f of B gives me f of B C, f of A give me f of A C. I can just uniquely map it to a pair f of A C, f of B C to just the product of both of A and B. And then my pi of A and pi of B here are just projections. So pi of A of AB just gives me A, pi B of AB gives me B. And the important thing is that this map here is unique. And so you can think of it as any other map can get factored for it, like in this way. And so any extra information, like the product has all the minimum information about your map F or your pairs of maps. And so any other map and like any other object C that has these maps just has just extra information that can be factored out. And so yeah, I mentioned so sets is Cartesian products in like Haskell types is just tuples, so pairs. And then I mentioned something about like the idea of duality. Well, I have products, I have a dual, like a mirror version of products called a coproduct, and it's obtained by reversing the arrow. So here, instead of my arrows going from A times B to A and B, my arrows go from A and B to A plus B in this case. And so I want this to be a coproduct, so I need for any other object C, if I have f of A and f of B like this, then I need a unique map from A plus B to C. And so in sets is just the disjoint union. So that's not the best example, at least in this case, but for Haskell types or just programming in general, it's actually fairly straightforward. It's just unions or enum. So A plus B is just an object of type A or an object of type B and nothing else. And so basically F is just a map that takes either an object of type A or an object of type B, and depending on the actual type of what it receives, apply either f of A or f of B. And so, for example, in Haskell, we call that either A, B, and it's either an object of type A or an object of type B. But we don't need to talk much more about some types. Okay, so we have products, and let's say that in my category, I can take all finite products of objects. In this case, plus some extra conditions, I have what it's called a Cartesian category because I can take all finite products. And a generalization of that, but let's not go too deep into that. So is the idea of a monoidal category is that okay, I can take products of my objects, and let's say I have also a special object that doesn't really add any new information. Then I have what's called a strict monoidal category. And so it's a category of a functor, so O times, that basically takes two objects in my category and return a new object, the product, and have a unit object such that so my monoidal product is associative, so A O plus, so yeah, I won't read through the whole thing, but this should be interpreted as basically any object of this type can be mapped to an object of this type. So let's say I have A, uh, comma B times C. In this way, I can trivially map it to another tuple of this type. And then the identity should not add any information. And so in Haskell, it's just an empty or unit object. And so in Haskell, it's usually represented as just empty parentheses. It's an object, but it does not do anything. And so clearly the tuple A with empty object is equivalent to A, and it's equivalent to the tuple with empty object A. And so back to what I was saying before, so if I have finite products, so like Cartesian category, uh, I have a monoidal category. So another example of like monoidal categories is tensor products. So if you have like tensor products of vector space and tensor product of linear maps, that's also a monoidal category. And monoidal categories are in general are very useful because you can do a lot of things. But let's get on to the actual application. So gradient-based learning, we want to be able to model, let's say as a program, machine learning models that are trained by gradient descent. And so to do that, we need a few ingredients. So first of all, we need parameters. Obviously, that's what we train. We need data. We need the ability to take gradients or like perform backpropagation, and also the ability to perform gradient updates or parameter updates. So I need parameter updates. So, and because we're doing programs, right, we really want programs that take parameters, data, and so on, and modify them using gradient information. And so I'll basically go through the main constructions of the first paper about how exactly to model that using category theory. And so first, let's add parameters. So for a strict monoidal category, the paper defines uh, a new category called para-C, and para, you should think of it as a functor, right? It takes a type or a type ecosystem and gives me new types. And basically, it's the category of parameterized maps over C. And so the objects are the same as the objects in C, And the arrows are maps with parameters. So I need a pair P, which is an object in C, that's my parameters, and a map F. And F needs to take a parameter or yeah, a parameter object, an input A and output some B. And so this would model, for example, a neural network that has some set of parameters, takes some set of inputs, and computes an output. Um, and then the identity in this case is simply my monoidal unit coupled with the identity on A. But that's not too important. And then the more difficult thing to define is how to compose these parametric maps. Um, I have like the algebraic definition here, but it will be, I have a clearer example or clearer definition on the next slide. Um, so if I take Pf and then apply P prime G, so notice that this comma here is just another way to write the composition, and then it's more sequential composition. So if you read it using the normal composition operator, it's okay, Pf, and then compose with Pg, and then it's in this other way, it's more as if you were programming in like C, it's Pf, then P prime G. And then the composition is, okay, I need to combine both of my parameters, so I have P prime and P, and then my map here applies one, which is the identity to my P prime, it doesn't use it, then applies F, and so F is going to take P and an input, return B, and then G, apply G, and G is going to consume this P prime and the output of the previous step. But this is not the most clear way to write it. And one thing that is very nice about category theory, and like I think the most interesting, is that category theory has formally defined diagrammatic languages. And these are really useful for describing computations. And this is an example. So in this case, we're using string diagrams, which essentially describe how yeah, how some piece of computation is factored out. And the idea is that if I have f here that takes a and b, I show it at this. So input on the left goes into my box f, parameters on top uh, go to f, and then out comes an object of type b. And then composition is simply, well, this is my other lens, or not lens, my other parametric map. Well, I can just stick these two diagrams together and that's my composition. And you can actually check that the computation described in this diagram of, okay, need first I take A, it goes to F, P goes to F, I get B as an output, I take P prime, apply F prime, and then get back C. This is basically exactly the same, oops, computation as described in this case, but it's much simpler. It's like so obvious that you don't even need to really think about it. And so that's one of the strengths of category is that you can do this completely rigorously. So as another example of stuff we can model is reparameterization. Let's say I change the way my network is parameterized. Uh, then it's just having a box alpha that takes my new parameter space Q and maps it back to P, and that's it. And so I can represent my computations by like drawing these diagrams, boxes and arrows. So far so good, but now we need also to model how we can update, let's say, parameters or even inputs. So for that, we need something called a lens. And lens do model basically parameter updates. So for a Cartesian category C, so essentially I have finite products. Lens is another category, and it's basically another functor. And the objects here are pairs of A and A prime, and A you should think of it as my state, and A prime as my update. And most of the time, well, A and A prime are basically the same object. So, but we can distinguish them here. Um, and then arrows in this case, I'll basically have an arrow describing the forward pass and an arrow describing the backward pass. And so I have F and F star, and F is my forward pass, so it takes A to B, and we haven't added parameters in this case, but we'll add them later. So F is my forward pass, it goes from A to B. And then F star describes how I take a parameter update in my output and map it back to an update on the input. And so I need A because it was my original input, an update on B, and it outputs an update on A. And really, again, the like diagrammatic way of representing these is as the following. So I have A and A star for my input. A gets maps to F to give me output B, and it also gets routed to F star, and F star takes an update B prime and outputs A prime. And so how do I compose these like lens morphisms? It looks something like this. So the forward pass is very easy. It's just G composed with F. But the backward pass is a bit more hairy. But really, it's just what you get from this diagram. So if you look at the backward pass, well, first I need an update in C. It gets mapped into G star, and G star also needs to take a value of B, but to get a value of B, I need to get my object in A, get it through F, and then route it back here. And so this is basically what's happening here. Once I've done that, I get an update of B, which gets pumped into F star, and it also takes my input A in there, and then I get my update of A. And so if we write it for an input A C prime, I apply F star all the way at the end to A, and then here I need G star of F of A and C prime. So if this is a bit confusing, it's easier to just like write it down on paper and like think through it. But the point is that the category in this case describes all the syntax we need to describe this without anything else. So it's really the syntax. And this is interesting for compilers. Compilers basically manipulate this kind of stuff. Well, not literally graphs, but for humans, it's much easier to reason in diagrams like these than reason in expressions like these. But this is more useful for um, the compilers, and especially then if you have um, transformations that say, okay, this expression is equivalent to this expression, but is a bit faster, then you can let your compiler do stuff while keeping your program correct. Okay, so we had like parameters and we had like updates. We can now combine them. And the way we do that is fairly simple. We just apply the para functor to lenses. And so objects are still pairs of state and updates. And then arrows now also take parameters and parameter updates. And so my forward pass still takes parameters, input gives me an output. And now my update map takes a parameter and input, an update on the output, and returns an update of both the parameter and the input. And we can just draw them as like these boxes, which is essentially the same. And so now we have parameters and updates on these parameters. So far so good. So now comes in the like gradient stuff. And at least in the first paper, the way we do that is we assume we have a functor for each map f. Well, it's not exactly a functor, but I have a map that's to each map or each morphism from A to B. I obtain essentially the backprop operation of f, which takes A, an output or an update to B, and give me an update to A. And really, this is just backpropagation. And if you look in the paper, they give full axioms of what this R operator needs to satisfy in order to be a differential operator, as in like it literally just does backprop. And if you represent it as a diagram, it looks like this. It's just use this backprop operator as your update operator. And in this case, it makes sense, right? Because the derivative need also is defined at a certain point, so we need also the original input in order to compute the derivative. So far so good. So we have parameter updates via backprop. And if we put almost the whole thing together, we can describe models as parametric types. So in this case, if I have like my forward pass looking like this, so A goes through F with parameter P and outputs B, then the full like update mechanism I need for training looks a bit like this. It's a bit scary, but it's basically just the combination of what we've talked about before. So A, I need A and P, it gets mapped to C to input, it maps as input to F, output is B. And then if I have an update to B prime, I need to map it to the backprop operator, which also takes the inputs and the parameters as inputs, and it outputs a parameter update and an input update. But notice that I don't necessarily need to do anything with these updates, depending on what I want to do. So the model now looks a bit like this. And we can actually model a bunch of other things with this framework of lenses. So let's say the loss function, for example, right? The loss function, if we were doing supervised learning, well, we're comparing the output of our model. So this is the model. It gives me an output, and I'm going to compare it with like the ground truth. And so this would be like if this comes from your dataset, this comes from the dataset, and we want to compare the output of the model with the ground truth. And that's basically what the loss function does. And so the loss function takes the ground truth and the model output and gives me some value. And then in the paper, they close this off using some map. I'm not going to go into details, but they say we can model learning rates this way. And it feels a bit of a hack, but it works. But like roughly this might not be essential. But in this case, okay, we say the learning rates depends on the loss. Maybe, maybe not. And then I use that to get a loss update, which then gets okay, fed back into the loss to compute the gradient of the loss, and then that gradient gets passed on to the model to get the essentially backpropagation, and then all the way to the left. But notice that okay, we had just the nice thing about this is that we just have like a bunch of different components that get pieced together without like much hassle. But again, this is just pure syntax. And it turns out that also optimizers, we can describe it this way. So if especially specifically we can describe optimizers as reparameterizations. This is a bit hairier, but the idea is that okay, we have the model that okay, gives outputs, takes updates, and then it sends like parameter updates. And then what it does with that is depends on the optimizer. And so roughly, we can also describe like an optimization diagram as a lens. And let's give the simplest example of like a gradient update. Um, a gradient update is going to be a lens here, and it takes, so let's say here just parameter pairs of parameters and maps it. I think this should be p prime. So it takes parameter values and parameter abilities and just adds it. So g of p in this case, so applied to the forward pass is just the identities, just the values of my parameters. And then the update operator, well, it takes p and then an update p prime, and it just adds them together. And remember, because we have only the learning rate included into the backprop, this is the whole gradient update described here. That's gradient descent, but if we want to do more complicated optimizers, we can do that. We just need to add some extra state to this length. So a more stateful parameter update is going to have some state s in addition to the parameters, and then we just need to define the operators correctly. So for example, momentum, so the forward pass is just, again, gives the parameters, and then the backward pass, well, it has a state which contains the momentum, the parameters, and the parameter updates, and it computes s prime being minus gamma s plus p prime, so that's the update of the momentum. Then the new momentum value is just s prime, and then I add it also to the parameter. And so that describes momentum. If you look back into the paper, they give a lot more example of how to do Nestrov, descent, Adam, and so on. So all of these optimizers can remodel, describe them in this way. And okay, again, this is not necessarily interesting if you're trying to build a model, but it's interesting if you're trying to compile them. So we can sort of get a full picture of like what supervised learning looks like. And we have just a box that's our model, which could be like multiple boxes composed of each other. And here it's supervised learning. So I want to take my dataset that goes through these two nodes. So I need my like data inputs and data ground truth. The inputs get mapped into the model with some parameters. I get an output. It gets mapped to the loss function, which gives me a loss value for the model output and the ground truth. Then the loss function gets mapped into the learning rate in this case. Let's assume it's constant or whatever. And so this returns me a loss, a loss update, or essentially the derivative. It gets mapped to the loss, and then the loss should it produces an output to the like this here, but we don't really care about this. We don't really want to change the ground truth. So in this case, this gets just mapped to a dead node and doesn't do anything. But we also get the loss on the model output, which gets fed back into the model. Then the model does its output, its update map, and sends an update to the optimizer. The optimizer does its thing, and then it can also send an update to the input. But in this case, we also don't want to change the input, so it just also gets mapped to nothing. But in the paper, they show how, okay, if instead you wanted to optimize the input, you could do that using exactly the same approach. And so like this, assuming like my boxes here are a bit more detailed, those describe essentially all the components of my network plus training plus backprop in a purely syntactic manner. And so again, this is interesting if you just want to like compile this representation to something that correctly gives you the your model and trains it. Okay, any questions before we move on? Okay, I guess not. Um, I think I'll do what I intended to do to finish, and then we'll see if you have more questions. So I wanted to have a crack at explaining the joke or the meme. A monad is a monoid on the category of the functors. And it's not as difficult as it seems. But recall, like we had this idea of list, the list monad. Uh, So list of A, right? It's a functor. List is a functor that takes a type and gives me a new type. So list, I can think of list, the list type as a functor that takes types and returns a new type called list of A, and it's just the types of lists of this type. Now, I can ask, okay, what happens when I apply this functor multiple times? Like, what happens if I do list of list of A? What happens? And like, maybe can I do something about this? And so we've talked about the idea of a monoid before, but mathematically monoid, it's like a set M with some kind of product star and then an identity. And the idea is that I can there's not a lot of needed, so I can take products, monoidal products of like items in M. That's my operation, and the rule is that this should be associative. So A star B star C is the same as A star B star C. And then the identity just means that I star A is equal to A is equal to A star I. The whole idea of like a monad is a monoid on the category of functors is first, well, list it's a functor, but it's a functor from Haskell types to Haskell types. So it maps into the same category, which is why it's called an endofunctor. And then the monad part, the monoid part, comes from mapping uh, my list functor multiple times. So list of list, I can think of that as composing my, it's like list times list of it. So like I can compose my functor list. And now, and it's easy to see that it's basically it already has this associativity condition. I just need to find a unit to make this a monoid. And so a unit in this case means I need to be able to map from A I need a natural way to map to list of A, and it needs to do so in such a way that if I have, let's say, F from A to B, and this way, I need to be able to like have an equivalent list of F here. And the way this works, like if here I just need an object of type A, and here would get F of A, just to get a single one. So the natural way to like embed my types, object of type A into list of A is just taking singletons. So A here would just get mapped to the list with one element, little a. And then F of A would get mapped to the one element list, F of A. And so this might be not as good as I intended, but the fact that I can map like object of type A straightforwardly to object of type list of A, that is my monoidal unit. And then the composition is basically composing list. And basically I need to be able to turn list of list back into a list. And the idea of that is doing a flat map. So this is just flat map, which is just concatenating my lists of lists. Okay, that was probably not as clear as I wanted, but I think I'm not going to make another attempt. Um, any questions? Okay, lots of half-formed questions need to process a bit. That makes sense. In the meantime, I go through some of the examples in here. So because they had a lot more examples of how to do optimizer, so really like the examples makes it much less abstract. Is that from one of the readings? So some of the examples I gave were based on the book by Awoday. Like in general, it's a great book because it's both math and computer science because the book is for both math and computer science students, and so they have a lot of examples from lambda calculus and that sort of stuff. Otherwise, you can look at the course slash book from Milevsky. He's a lot more into the functional programming side of things, and so he uses Haskell a lot for examples. But yeah, the examples I mostly took inspiration from those two sources. Although the later ones I took them from this paper here. Um, yeah, so I just wanted to go back to the examples here. So they have the gradient update as just p plus p prime, and then p prime already has the learning rate baked in. And then for stateful, they show, okay, momentum looks like this. So I compute my momentum term and then update my momentum and update my parameters. And then nest-raw is a bit funnier because you have like some kind of look ahead. And yeah, we have Allegro and Atom, but they are a bit more involved, but it's still the same idea. Okay, yeah, I don't think we'll go through this at all, but I sort of talked about it in the earlier, but this is much less easy to get into. But so beware. But anyway, I thought it was like interesting enough to talk about these things.